The foundation of quantum mechanics has been rejected by experiment. The foundation we're talking about here is the interference experiments. Young's double slit interference experiments may be explained by particle photon models rather than wave models, and that's what rejects quantum mechanics foundations. Particle experiments, such as the photoelectric effect, have difficulty with wave models. A particle model of light rejects quantum mechanics, so a photon model of the interference experiments that also reject wave models of light. Quantum mechanics calculates probabilities and correlations, whereas the theory we're going to talk about here, the scalar theory of everything, suggests all effects are related to all other effects. This theory is causative and Machian, which no other theory is. Because the causal links may be complex and not time coordinated, correlation may appear small. The weirdness of quantum mechanics is unnecessary. Quantum mechanics should be restarted from a causal perspective. Left unexplained is how a photon model of light could model interference experiments. Thus, the photon model was used to develop a computer simulation program from Scalar Theory of Everything postulates. These postulates are that all action are action by contact. Bestow postulates are causative, they are not probabilistic. Hods cause warping of the plenum, and the plenum waves direct the hods with a speed much greater than the speed of light. And the postulate suggests a Machian interpretation. Particles, that is to say hods, have a definite position and momentum at all times. Uncertainty is in the measurement. The best measurements can do is plus or minus 1 hod, which has an energy of Planck's constant. This is the cause of the uncertainty principle. The plenum density has a definite amplitude through all space, and it supports wave action. This is the symbol for plenum density. We suggest a universal equation where we calculate the plenum density at all points in space from spiral galaxies, elliptical galaxies, and of course all the matter in the universe. The gradient of the plenum density gives you a force on each hod. This is how we apply it to interference experiments. All the rest of the universe, other than the small table on which the experiment is conducted, produces a constant plenum density across the experiment. And then all we have to worry about is simply the hods in a local environment, meaning in the photon and in the table and mask and screen. Photons are particles, which are a column of hods. So here we have our column of hods. And as they move through the plenum, they produce waves in the plenum. This is the direction the photon is moving, and this is angled to the side of the photon's trajectory. And you see that the photon is producing a variance, peaks and valleys of waves in the plenum. So here we have a photon that is between a mask and a screen, and there's the slit in the mask. The waves from the photon go out, reflect off mask and screen, and are reflected back to the photon, which then directs the photons. Here's a look where we take the simulation that we developed, where we trace one photon at a time through a single slit experiment. So here's the photons, there's the slit. First, you'll notice that the photons tend to go towards the edges of the slit. which has been noticed by some experimenters. You'll also notice that as they go away from the center, they become more concentrated, that is to say brighter, near the edges of the slit. This also has been noted by some experimenters. What has not been noted is that from there, the photons then cross the center line of the experiment. So here is the developing center maxima and the other peaks. This is a simulation of a one-slit experiment. These little dots here are the result in a given bin. The solid line is the Fraunhofer diffraction pattern calculation, and you'll notice that the bin counts that we get here in the simulation are a very close match for a Fraunhofer diffraction pattern. Here's the same thing for a double slit, and of course the simulation, where you'll note that these peaks that you see here are just the interference fringes within one diffraction pattern. The simulation is used to explain the transparent mask experiment, the double slit experiment, and the Afshar experiment. Okay, so here's the paper about the transparent mask experiment. We start with a laser producing a light. We send it through a mask with a single slit and then onto a screen. And this is the image you get. You notice this is a diffraction pattern. We next place a piece of glass between the first mask and the screen. This becomes a second mask, as we call it. And you'll note that the diffraction pattern is the same. The similarity suggests the glass is not causing the interference effects we're going to note here. So the next step, we need to note something. Here we have a second opaque mask with a slit, and there is the position of that second mask onto the first slit pattern. You'll notice that what you get is a diffraction pattern, not an interference pattern. In our transparent mask experiment, the second mask is two pieces of glass with a small gap between it. This then is a transparent mask experiment. And what you get is an interference pattern. You will note here, these are interference fringes. The next step is to block the light going through the slit by a nail. If we place the nail such that there is light on both sides of the nail, then what you get is interference pattern behind the nail. And this is the trick. What we have to do is place the nail such that the edges of the nail are right at the minima of the first slit diffraction pattern. And what you'll get is no interference pattern and a blockage of the light directly behind the nail. So here is that version. And you see we still have the interference fringes just like before, and we have no light coming through the slit. With no light going through the slit, you then reject the wave models of light. And of course, it's the presence of the slit that causes these interference fringes, but it causes them after the photon has passed through the mask, out through the transparent mask. This is the simulation of the C version that we talked about. Here, the bins that count the photons are kind of big, so it kind of mushes this out, but we can make the bins smaller, and therefore we can then see the interference fringes. Here's the simulation of the D experiment. You'll note there's no photons in the middle where the nail is blocking the light, but the remainder looks pretty much the same as before. The Afshar experiment is an experiment that recovers the which way a photon goes through the slits, that is to say, which slit it goes through. And in that, they reject the Copenhagen interpretation of quantum mechanics. What they do is they keep track of the angle the photons are going, which we can do really easy because it's a computer simulation. And then when they reach the screen, we simply record and plot the angle versus where it is on the screen for photons going through one slit and the other slit. We then take linear regression, and what we find out is that they are headed in slightly different directions. And that then is how the Afshar experiment works. In conclusion, the transparent mask experiment rejects wave models of light. Also, the basis of QM is rejected also. The toy simulation of photon interference explains both the wave supporting experiments and the wave rejecting experiments.